Welcome back. In this video we're going to be concentrating on the alkanes, and we're going to be starting by looking at structural isomerism. So we're on page 12 of your notes and we're looking at the three simplest alkanes: methane, ethane and propane. Now there's only one structure for each of these molecules. So if you have 3 carbons and 8 hydrogens, you can only make a propane molecule. However, once you get above C3, once you get C4 and above, you can get different structures, and we call these structural isomers. So these are compounds which have the same molecular formula, in other words the same number of carbons and hydrogens, but they have a different structure. The one we're going to be looking at first is what we call chain isomerism. So this is a different arrangement of the carbon chain itself. And for C4H10 there are 2 structural isomers. So the first formula we have is just the straight chained butane molecule. So I have 4 carbons in a sort of zigzag pattern, because the bond angles are not 90, they're actually 109.5. So that's one structure. Skeletal formula, quite easy. 1, 2, 3, 4 carbons. But there's another way I can arrange these carbons and hydrogens, and that's to have 3 carbons in a chain, but a methyl group on that middle carbon. So I'm having a branch on here, which is why this is called a chain isomer, because now it's got a branch on it. Same number of carbons and hydrogens, just different structural formula. So again, if I do the skeletal formula, I've got 3 carbons now, so 1, 2, 3, and I've got a methyl group on that second carbon. Doesn't matter if I point that line up or down, it means the same thing. So this is called butane. But means I've got 4 carbons in my longest chain. Ane tells me it's an alkane. In this one, I've got 3 carbons, so that's propane, but I've got a methyl group on that middle carbon, and therefore it's methyl propane. I don't technically need the 2 there because there's only one position for that methyl group to go. If I was to put that methyl group on the carbon on the end, that would just extend the chain by 1 and it would make butane again. Structural formula, remember you're reading them across the page, so I get CH3, CH2, CH2, CH3, and this is a straight chained molecule. Reading this one across the page, I get CH3, CH, but it's got this CH3 group, so I'm going to put that CH3 group in a bracket to show it's a branch, and then I've got a CH3 group on the end, and that obviously is a branched molecule. So you can pause the video at this point and have a go at the examples on the next page. So on the next page I have the 3 isomers with the formula C5H12. You can see here I have my straight chained pentane, and then I have 1 branch to make 2-methylbutane and 2 branches which will make 2,2-dimethylpropane. And drawing the skeletal formulas of the isomer C6H14. This case there are 5 of them. Again, we start with a straight chain. We've got 2 which are mono-substituted, so I've got single methyl groups on them, and then I've got 2 with 2 methyl groups on them. You should notice that as the number of carbons increases, so does the number of possible structural isomers. So we're on to page 14 of your notes, and we're going to look at the alkanes in a little bit more detail. So firstly, we're going to look at their physical properties. So we're going to look at the boiling points. But before we do that, we need to understand the general formula. So this is the general formula for an alkane, and they all fit this pattern, CnH2n plus 2. They are all hydrocarbons and they are all saturated molecules. So there we have the first 10 straight chained. Side we have their boiling points. So what we'd like you to do now is to pause the video and have a go at plotting the number of carbon atoms versus the boiling points of the straight chained alkanes. So here I've plotted the number of carbons versus the boiling points. And as you can see, there's a gradual increase in the boiling point of the alkanes as I increase the number of carbon atoms in my chain. So this is telling me that as I add carbons to my chain, as my molecule gets longer, the boiling point gets higher. In other words, the intermolecular forces between the molecules are going to get stronger the more carbon atoms I have in my chain. So we can say that the intermolecular forces of attraction, and these are what we call London forces, are stronger in larger molecules than they are in the smaller molecules. The reason for that is the London forces are stronger. The reason the London forces are stronger is because you have more electrons, and London forces are primarily dependent on the number of electrons present in your molecule. And we're going to study more of those later on this year when we look at intermolecular forces in more detail. So on the next page of the notes, we're looking at two isomers of pentane. We're looking at 2-methylbutane and 2,2-dimethylpropane. They both have the same numbers of carbons and hydrogens, but they have slightly lower boiling points than their straight-chained counterpart. And the reason for that is branching. So the more branches a molecule has, the lower the boiling point is going to be. The reason for that is there are weaker forces of attraction because the molecules can't pack efficiently together. So with these molecules here, they have these big sticky out bits, and that means the chains can't pack as efficiently or lie as closely together. It reduces the points of contact and therefore reduces the boiling point. But we'll study that in a lot more detail when we look at intermolecular forces. The last thing you need to be aware of is the fact that the alkanes are insoluble in water. They don't mix with water. So hexane, which is our example of an alkane, will form two layers when you add water. Ethanol, which is not an alkane, it's an alcohol, and it forms a single colourless solution. It's highly soluble in water. Doesn't matter if it's a cyclohexane, a cycloalkane, or an alkane. Neither of them will be soluble in water. Again, this is something we're going to study in more detail when we look at solubility later on this year. So that finishes this section of the notes, just introducing you to alkanes and looking at the two physical properties you need to understand. The change in boiling point as you increase the carbon chain and as you increase branching, and also the fact that they're insoluble in water. In the next section, we're going to go on and look at alkanes as fuels. So until then, take care, stay safe, bye-bye.